Here's a video for note 6-6, transformations in vertex form. So to understand transformations in vertex form, we need to understand what the parent function is of the quadratic. The parent function of a quadratic is y equals x squared. This is the most basic quadratic ever, with the vertex at 0, 0, and a being a value of 1. So we can plot our parent function here by basically plugging in points. Well, if we know our vertex is 0, 0, we know that that's our first point, 0, 0, and then we can plug in the value of x equals 1. Well, 1 squared is equal to 1, so that point is 1, 1, and then we can use the fact that a parabola is symmetric to plot the other point. Then we can plug in 2, 2 squared is 4, so 2, 4 would be our next point, and then we can use a symmetric point to plot on the other side, and then we can plug in 3, 3 squared is 9, so the next point would be 3, 9, and then again using symmetry to plot my other point. So when we're talking transformations in vertex form, we're talking how does a parabola change in relation to our parent function y equals x squared. So here we have a quadratic written in vertex form, y equals a parentheses x minus h squared plus k. In previous lessons, we've learned that a affects the concavity of our parabola. We know that h is the x-coordinate of our vertex, also the axis symmetry, and k is the y-coordinate of our vertex. But what we're going to learn today is how a, h, and k are in terms of transformations from our parent function y is equal to x squared. So remember, our parent function, or f of x equals x squared. Our parent function is basically 1 x minus 0 squared plus 0, which simplifies to y is equal to x squared. So our parent function has an a equal to 1, an a equal to 1, and an h and k equal to 0, 0. So what we're going to learn basically is how does changing the value of a, h, and k affect our parent function in terms of transformations. So we know that the value of a affects the concavity, but in terms of transformations, we're going to refer to that as a reflection. So we know that when a is positive, we have a graph that is concave up, but we would call that that there's no reflection, because again, we're referring back to our parent function y equals x squared, which we know is a parabola that faces up. If a is negative, we know that that's concave down. In that case, we say that there is a reflection across the x-axis. So our parent function, y equals x squared, is reflected over and faces down, which would make it concave down. What we haven't discussed yet is how changing the value of a actually affects the parabola in terms of what it looks like. Well, we know that when a is equal to either positive or negative 1, we're going to say that there's no stretch or compression. Because again, going back to our parent function, y is equal to x squared, if a is equal to 1, remember in our parent function, a is equal to 1. So if a is equal to positive or negative 1, there's not going to be a stretch or compression. A is also going to affect the width of our parabola. When the absolute value of a, so ignoring the sign, because we know the sign just affects whether it's reflected or not, when that's less than 1, or sorry, greater than 1, we say that there's a vertical stretch, which makes our parabola more narrow. You can think of kind of like pulling a rubber band. So it's more narrow than our parent function. When we have an absolute value of a less than 1, like a fraction like 1/2 or 1/3 or 0.7, our parabola is wider. We call that a vertical compression. So it's going to be wider than our parent function f of x equals x squared. So that's how changing the value of a affects the parabola. It tells us two things. It tells us whether or not there's a reflection. If a is positive, there's no reflection. If a is negative, there is a reflection across the x-axis. And then a also tells us whether there's a stretch or compression. If a is equal to 1, positive or negative, we would say that there's no stretch or compression because it's the same as our parent function. If a is greater than 1, we say it's more narrow. That is a vertical stretch. And if a is less than 1, it's wider than our parabola. We would call that a compression. So the next value is h. Well, we know that h is the x-coordinate of our parabola. However, changing the value of h actually gives us a horizontal translation. So when h is negative, we have a horizontal translation left. And just remember, it's the opposite sign for h. So in our parentheses, it's actually going to look like x plus h. And then when h is negative, or when h is positive, sorry, we have a horizontal translation right. And again, the sign is going to be opposite when it's inside the parentheses. So horizontal translation left when h is negative, horizontal translation right when h is positive. The last value we look at is k, and that's going to be a vertical translation. So that's going to be the same sign. We know that k, it translates up when we have a positive k, and down when there's a negative k. And it's the same sign as whatever it is in the equation. All right, so let's look at our first example here. So it says using a, h, and k, describe all the specific transformations it would take to go from f of x equals x squared to f of x equals negative x minus 2 squared plus 3. Then we're going to graph the function. So first thing we're going to do is we're going to identify a, h, and k. So a in this problem is going to be negative 1. And remember, a tells us two things. So the fact that it's negative tells us that we have a reflection across the x-axis, which means we know that it's going to be concave down. And then since a is equal to positive or negative 1, that means there's no stretch or compression. Meaning it's basically going to be the same width as the parabola currently is, our parent function currently is. All right, next value is h. So h, we look inside the parentheses and it's the opposite sign, so it's going to be positive 2, which means we have a horizontal translation. Since it's positive, we're going right 2. And then lastly, k is positive 3, which means that we have a vertical translation up 3. Okay, so now let's go ahead and graph it. First thing we're going to do is we're going to go ahead and plot our vertex. So we know our vertex is going to be 2, 3. And we can also think of it in terms of a translation. So here's our parent function. So from our parent function, we're going to translate right 2, 1, 2, and we're going to go up 3, 1, 2, 3. So right 2, and then we're going to go up 3. So that's going to be our vertex. So again, there's our translations, right and up, and we have our vertex. So next thing we're going to do is we're actually going to use the value of a to plot our other points. So we know that we can plug in points to graph our parabola. We know our parabola, since it's facing down, it's going to look something like this. But instead of plugging in points, we're going to use this value of a and the fact that our parent function is graphed here to graph our parabola. So remember with our parent function, when we graph our parent function, the first point we do from our vertex, we go over 1 and then we go up 1. So from our vertex, we go over 1, up 1. That gives me my first point. Then the next point, we go over 2. 2 squared is 4. We go up 4. So over 2, up 4. That would be our next point. And then we would go over 3, up 9. Over 3, up 9 gives me my third point. That's our parent function. Well, we know that our transformation in relation to our parent function, the only thing we're changing is that it's concave down. There's a reflection. So instead of going up, we're actually going to go down. So when we have an a value of negative 1, we know that we're going to go down. So we're basically going to graph it the same way. We're going to go over 1 from our vertex, but instead of going up 1, we're going to go down 1. Then we're going to go over 2. We're going to go down 4. And over 3, we're going to go down 9. So from our vertex, we're going to go over 1, down 1. So our first point is going to be at 3, 2. And once we have that point, we can use our symmetric point to graph another one. So the next point, we're going to go over 2, 1, 2. And since there's no stretch or compression, just a reflection, we're going to go down 4. 1, 2, 3, 4. So my next point is going to be right here. And we're going to use our symmetric point to graph it. And then we can go over 3, 1, 2, 3, and down 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And again, using my symmetric point, I have it there. So now we're going to go ahead and connect our points. This is f of x equals negative x minus 2 squared plus 3. And this is our parent function, f of x is equal to x squared. So as we can see, we know that our vertex has been translated, and then the only transformation we did was we reflected it, so it faced down instead of up. All right, now let's take a look at example 2. So again, first thing we're going to do is we're going to identify a, h, and k and describe the transformations. So a is equal to positive 2. So since it's positive, that means there's no reflection, meaning it's going to be concave up. However, since a is 2, that's greater than 1. So in relation to our parent function, that means there's going to be a vertical stretch of 2. H is going to be negative 3 because we look inside the parentheses, it's the opposite side. That means it's a horizontal translation. And it's negative, so we're going to go left 3. And then K is going to be positive 1, which means that we have a vertical translation, up 1. All right, so in this particular problem, I don't have my parent function graph, but we can easily graph it, starting at our vertex, 0, 0, and then using 1 squared is 1, 2 squared is 4, 3 squared is 9, and then we can just reflect it over. You don't have to graph your parent function. However, it is kind of nice to have it there because it gives us something to compare our new graph to. So here's our parent function. So I'm just using kind of a dotted line. So this is f of x is equal to x squared. So based off our transformations, I know that I'm going to be shifting it left and up. So this problem is going to go left and up. There's no reflection, but there's a stretch, which means that my newly graphed parabola we know should be skinnier than our parent function. Okay, so now I'm going to go ahead and graph my vertex. So from my vertex, I'm going to do my translation. So I'm going to go left 3, and then I'm going to go up 1. And I'm going to go ahead and plot my vertex. And then from here, I'm going to use the a value to graph my the rest of my points. So remember my parent function, we went over 1, up 1, over 2, up 4, over 3, up 9. Since I have an a value of 2, that basically means I'm going to stretch the vertical distances by 2. So I'm going to double the distances. So instead of going over 1, up 1, I'm going to go over 1, up 2. I'm going to go over 2, instead of going up 4, I'm going to double the distance. And then 3, I would go up 18. So that's probably going to take us off the graph. All right, so from my vertex, over 1, normally with no stretch or compression, I would go up 1. But since I'm doubling my distance, I'm going to go up 2. So my next point would be right here. And again, we're going to use our symmetric point to graph its twin. Next point, I would go over 2. Normally, I would go up 4, but I'm going to double my distance. So I'm going to go up 8. So 1, 2, 3, 4, 5, 6, 7, 8. And again, I'm going to use my symmetric point to graph it there. Since we know that we can't go over 3 up 18, I'm not going to graph that point because that's going to take us off the graph. So I can go ahead and connect my points here. So here's my graph, f of x equals 2, x plus 3 squared plus 1. And it looks how we would suspect. There's no reflection, so it's going in the same direction. However, it is skinnier than our parent function, f of x equals x squared. All right, now for our third example. So we're going to identify a, h, and k. A is negative 1/2, which tells me two things. It tells me that there is a reflection across the x-axis because it's negative. Which means our graph is going to be concave down. And the 1/2 tells me that there's going to be a vertical compression of 1/2. So we know our graph's going to be skinnier than our original parent function. H is +4, which means we have a horizontal translation, right 4. And then K is -2, which means we have a vertical translation, down 2. All right, so I'm going to go ahead and graph my parent function just so we have something to reference as we're graphing it. Again, not necessary, but kind of nice to have to make sure that our graph looks correct. So we know our parabola is going to be wider than this graph and in the opposite direction, since we have a reflection as well as a compression. All right, so first starting with my vertex. My vertex is 4, -2. So from my parent function, I'm going to go right 4, down 2. So there's my translation. And then we're going to use the value of a in our parent function to graph the rest of my parabola. All right, so my parent function, we go over 1, up 1, over 2, up 4, over 3, up 9. But then we're going to use the value of a, which is -1/2, which tells me that we're going to go down, and we're basically going to go down half as much. So we're going to multiply these by 1/2. So instead of going up 1, we're actually going to go down 1/2. Instead of going up 2, we're going to go down, or sorry, up 4, we're going to go down 2. Instead of going up 9, we're going to go down half as much, which is going to be 4.5. And then we can go further if we want, but that should be enough to graph our parabola. All right, so from my vertex, I'm going to go over 1. Since there's a reflection, I'm going to go down, and I'm going down half as much since there's a vertical compression of 1/2. So I'm going to go down 1/2, which would put me right here. And I'm going to use my symmetric point to graph its twin. And then from my vertex, I'm going to go over 2. Normally, I would go up 4. Since there's a reflection, I'm going to go down. I'm going to go down half as much. So I'm going to go down only 2 units, which would put me right here. And then I'm going to graph its symmetric point. And then from my vertex, I'm going to go over 3. Normally, I would go down 9, but I'm going to go down half as much. So 1, 2, 3, 4.5 would put me right here. And again, using its symmetric point from there. So this is what we would expect because we know that a compression makes our graph wider than the parent function. And this graph is definitely wider than our parent function that we have here. So this is a wider graph. So let's go ahead and label this one. This is f of x equals -1/2 x minus 4 squared minus 2. And our parent function is f of x is equal to x squared. All right, so now for example number 4, we're basically going to be going the opposite. We have a parabola that is graphed already, and we need to determine what is the equation and what sequences of transformations it took to get to that parabola. So first thing I'm going to do is I'm going to start with h and k. Well, we know that our parent function, the vertex, is at 0, 0. So from 0, 0, we can see that our parabola clearly went left 3, and it went down 4. So that's going to tell me that h is -3, which means we had a horizontal translation left 3. And then that means k is equal to -4, which means we had a vertical translation down 4. So now to figure out our value of a, well, I know my graph is concave down, which means that there's been a reflection. So we know that it's going to be negative. So there's a reflection over the x-axis. So to see if there's a stretch or compression, let's look and see what our points are. So our first point is here. To get to the next point, we went over 1 and we went down, and it only took 1 unit to get to my parabola. So comparing that to our parent function, we would normally go over 1, up 1. So it seems the same as our parent function. Let's just check the next one. We go over 2. To get to our parabola, we would go down 4. And our parent function, that would check out as the same, which means that a is going to be equal to -1. There's no stretch or compression. It's the same width as our parent function. So there's going to be no stretch or compression. So now that I have a, h, and k, I can write my equation. It's going to be f of x is equal to negative x. Remember when we plug in h, it's the opposite sign, so it's going to be x plus 3 squared, and then minus 4 at the end. All right, so now let's look at the second example. So first starting with our horizontal translation. So to get to our vertex, it looks like we went right 4 and then down 4. So that means h is going to be positive 4. So we had a horizontal translation, right 4. And then k is equal to -4, which means we had a vertical translation, down 4. So now let's get the value of a. Well, our graph we can see is concave up, which is the same as our parent function. That means there's no stretch or compression or no reflection. So we know our a value is going to be positive. To figure out if there's a stretch or compression, let's look and see how our graph was graphed. So we're starting at our vertex. When we go over 1, it takes us 2 units to get to our first point. So normally in our parent function, we would only go up 1. In this case, we went up 2. So it looks like our stretch is 2. There's going to be a vertical stretch of 2. But let's just check our next point. We would go over 2. Normally we would go up 4, but it goes 1, 2, 3, 4, 5, 6, 7, 8. So it takes 8 units to get to my next point. So that's double the amount that it normally would on a parent function, which tells me that a is going to be equal to 2, which means that there's a vertical stretch of 2. And we can see that our graph is skinnier than what our parent function would be. So now that I have those values, now I can write my graph, f of x, or my equation, equals positive 2, x plus, or it's going to be minus 4 because it's the opposite sign, and then minus 4 at the end. All right, so now let's do just a couple of the practice problems. So here's our equation. So I'm going to first determine what a, h, and k is. So a is 2, so that means there's no reflection. Since a is greater than 1, that means there's going to be a vertical stretch of 2. H is going to be positive 3, which means there's a horizontal translation, right 3. And then K is -4, which means that we have a vertical translation, down 4. So I am going to go ahead and graph my parent function just so we have something to compare it to. Because we know that our graph should be skinnier than our parent function, but it is going to face the same direction. Since the concavity is the same, there's no stretch or there's no reflection. All right, so from our vertex, I'm going to go right 3, down 4. So I have my vertex. And then using my a value, my parent function. So for my parent function, We know that if a is equal to 2, that means we're going to double our vertical distances. So we're going to go up 2, up 8, and then up 18. So from my vertex, we're going to go over 1. Instead of going up 1, we're going to go up 2. So my next point would be right here. And again, we're going to find our symmetric point. Then I'm going to go over 2 and I'm going to go up 8. So 1, 2, 3, 4, 5, 6, 7, 8. I'm doubling my vertical distances. I'm stretching my parabola. And since our next point will probably take us off the graph, I'm going to go ahead and connect my points. And I'm going to label my graph. So this is f of x equals 2x minus 3 squared minus 4. All right, so now with number 3, I'm going to identify a, h, and k. So a is negative 1/2, which tells me that there is a reflection across the x-axis since it's negative, and it tells me that there's a vertical compression of 1/2. H in this case is negative 4, which means we have a horizontal translation. Left 4. And then K is negative 2, which means we have a vertical translation. Down 2. All right, so graphing my parent function. We know my graph is going to be facing down, and it's going to be wider since there's a compression. So first, plotting my vertex, I'm going to go left 4, and I'm going to go down 2. So I have my vertex. And then with my parent function, over 1, up 1, over 2, up 4, over 3, up 9. But since our a value is negative 1/2, we know that we're going to go down, and we're going to go down half as much. So down 1/2, down 2, and down 4.5 from our vertex. So from the vertex over 1, we're going to go down 1/2. So my first point is going to be right here. And then we're going to use find its symmetric point. And then from our vertex over 2, normally we would go down 4, but we're going to go down half as much since there's a compression. So that would give me this point right here, and its symmetric point. And then from my vertex, I would go over 3. Normally I would go down 9, but we're going to go down half as much. So 1, 2, 3, 4.5, which would give me its symmetric point right here. So negative 1/2 x plus 4 squared minus 2. All right, so now a couple of the working backwards problems. So starting with problem number 6. So first thing I like to do is to start with the vertex. So remember that our parent function starts at 0, 0. So to get to the vertex, it looks like we went right 2, down 3. So that's going to give me my h and my k. So h is positive 2, which means there's a horizontal translation right 2. And then k was negative 3, which means that there's a vertical translation down 3. And then we're going to get the value of a. Well, I see that my graph is concave down, which means that our graph has been reflected. So we know it's going to be negative. So there's a reflection across the x-axis. And then to determine the value of a, we're going to see how this was graphed. So it looks like we went over 1 and we went down, so we know it's negative. We went down only one unit, which is the same as our parent function. So over 2, we went down 1, 2, 3. It took us 4 units to get to our parabola. So that's the same as our parent function, how we would graph it, which means that there's going to be no stretch or compression, which means a is going to be equal to 1 or -1, no stretch or compression. So now I have my graph, f of x, or not my graph, my equation. So -1, so it's going to be x minus 2 squared minus 3. All right, number 8. So again, starting with my vertex. So normally my vertex is at 0, 0. So to plot my new vertex, it looks like we went right 4, up 1. So that's going to give me my h and my k. So h is 4, which means it's a horizontal translation. Right 4. K is equal to 1, which means it's a vertical translation. Up 1. And then the value of a. So it's facing down again, which we know means it's going to be negative. So that means there is a reflection. And to me, just by looking at this parabola, it looks skinnier than our parent function. So to verify what the value of a is, I know it's going to be probably greater than 1. So to determine what the value of a is, let's see how it was graphed. So over 1, it takes us 1, 2 units to get to our graph. Normally on our parent function, it should only take us 1. So it looks like our a value is 2, but let's just check. For the second one, normally we would go down 4. But to get to our graph, we have to go down 1, 2, 3, 4, 5, 6, 7, 8. So I kind of counted that weird. 1, 2, 3, 4, 5, 6, 7. Yeah, it took us 8 units to get to our parabola. So that's double the amount that it would for our parent function, which means our a value is going to be 2, which means that there's a vertical stretch of 2. So now that I have that, I have my equation. So it's going to be -2 x minus 4 squared plus 1.